Hello viewers, myself is Dr. Vadiraj B. Tango, Assistant Professor, Sri Jagadguru Tontararia, Government Tertiary College, Mundagi. In this video, I am discussing about heat engine. In that, I am dealing thoroughly with the Otto engine and Otto cycle. This video is for BSc program, physics subject. It is for the second semester and the paper is thermal physics and fluid mechanics. I am mostly dealing about the Otto engine and Otto cycle. Before that, few discussions about the engines. Learning objectives of this session is to know the concept of heat engines, to understand the types of heat engines, basic necessaries for the working of engine, Otto engine, its construction and working, performance of the Otto engine, efficiency of the Otto engine. And outcomes from this session is knowledge of different kinds of engines, understanding of necessities for the engine, idea about the working of Otto engine, mathematical calculations for efficiency of Otto engine. Prerequisites for this discussion is concepts about efficiency, isothermal and adiabatic process, basics of Boyle's and Charles law. Syllabus prescribed by Karnataka University is heat engine, in that Otto engine, Otto cycle and expression for efficiency. Diesel engine, diesel cycle, expression for efficiency and Carnot's theorem. Now the question will be arises, what is heat engine? Heat engine is a device which converts heat into a mechanical useful work. Engines are classified into two types. One is called external combustion engine and internal combustion engine. In this external combustion engine, the heat will be developed at the steam chamber and it is transferring to the crankshaft. As a result, work is done outside from the steam chamber. Hence, it is called external combustion engine. Example is railway engine. Another kind of engine is internal combustion engine. Here, heat generated in the chamber. Immediately, it is connecting with the crankshaft. No transfer of work from one place to the another place. Therefore, such kind of engines are called internal combustion engines. Example, engine of car. And any heat engine consists of three parts. One is source at higher temperature T1 and very low temperature called sink T2, and very important is working substance. This working substance may be petrol, diesel, air and any kind of oils. If the working substance is petrol, it is called Otto engine. If the working substance is diesel, it is called diesel engine. And ideal kind of engine is called Carnot's engine. Heat engines and its cycles. Ideal engine and cycle is Carnot cycle, Rankine cycle, Otto cycle and diesel cycle. If the engine working as a working substance as a petrol, and that kind of engine is called Otto engine, and its a description on a PV diagram, it is called Otto cycle. This Otto engine has been constructed by in the year 1862 a German engineer Nicholas Augustus Otto. began experimenting with different kinds of engines. His first experiment was conducted on a four-stroke engine. 10 years later, he introduced the word the Otto engine. The four-stroke engine consists of a four-stroke cycle, better known as the Otto cycle. The Otto engine is an internal combustion engine. The four-stroke cycle, an IC engine, is a cycle most commonly used for automotive and industrial purposes today. It is used for cars, trucks, generators, and many more appliances, making this engine the most common engine type nowadays. In the Otto engine, it consists of many parts. Each part is essential for the stroke cycle to occur. The main parts of our four-stroke cycle engine are intake valve. Here we can pass the air and petrol. The exhaust valve, where the exhaust gases will be come out of here. This is inlet valve. This is here. This is inlet valve, and this is exit valve. So in this intake valve, we are passing air and petrol vapors. In the exhaust valve, the exhaust gases will be expelled from the chamber. The piston, this is piston, rings, here are the rings. The combustion chamber is all combustion chamber, the connection rod, the crankshaft, and the spark plug. So here the spark plug is there. These parts play an important role in the operation of the engine. And this Otto engine is a four-stroke engine. As the name implies, it is a four-stroke internal combustion engine which have four basic steps that repeat with every two revolutions of the engines: intake stroke, compression stroke, expansion stroke, and exhaust stroke. So the four-stroke engine, the engine parts are here. It contains intake valve. Here air and fuel mixture is passing. So here is a spark plug. This is exhaust valve. Here is the combustion chamber. This is piston, connecting rod, crankshaft. So this step is called intake step. This is called compression step. This is called power step, and this is called working step. So accordingly, the crankshaft will be moved up and down. Heat will be heated in the chamber. Spark will be sparked up with the spark plug. As a result, engine will be starts. So if the burning will be takes place, it releases the exhaust gases. The exhaust gases will be moved from the exhaust valve. Mechanical operation of Otto cycle. So first is ignition stroke. Intake valve and exhaust valve remains closed. First, if the process will be stops, both the valves must be closed. Ignition is given by the spark plug when the piston reaches TDC. Compressed air fuel mixture is ignited by the spark, starts burning. The gas expands in the cylinder, pushing the piston towards a crankshaft, generating rotatory power at the crankshaft. So that expression, that formation or dot process can be represented in a PV diagram with a step E to A. Intake stroke this is. The first stroke of the internal combustion engine is also known as suction stroke because the piston moves to the maximum volume position, downward direction in the cylinder, creating a vacuum, negative pressure. The inlet valve opens as a result of the cam lobe processing down on the valve stem, and the vaporized fuel mixture is sucked into the combustion chamber, the inlet valve of the end of the stroke. Intake stroke. Intake valve starts opening. Air fuel mixture is sucked in a cylinder through the open intake valve by the piston moving down the crankshaft. Exhaust valve remains closed. No ignition is given by the spark plug. It is represented by in a PV indicator diagram A to B. As a result, volume will be compressed. Temperature will be rises from T1 to T2. Compression stroke this is. In this stroke, both valves are closed and the piston starts its movement to the minimum volume position, upward direction in the cylinder, and compresses the fuel mixture during the compression process. Pressure, temperature, and density of the fuel mixture increases. In case of compression stroke, intake valve closes, air fuel mixture is compressed in the cylinder by the piston sliding away from the crankshaft. Exhaust valve remains closed. No ignition is given by the spark plug till it reaches the TDC. This motion from graph A to B. Power stroke. When the piston reaches a point just before a top dead center (TDC) top dead center, the spark plug ignites the fuel mixture. The point at which the fuel ignites varies by engine. Typically it is about 10 degrees before top dead center. This expansion of gases caused by the ignition of the fuel produces the power that is transmitted to the crankshaft mechanism. Exhaust stroke. The exhaust valve starts opening. Burned gas is pushed out from the cylinder to the opened exhaust valve by the piston moving away from the crankshaft. The intake valve remains closed till the piston reaches TTC, total dead center, that is T2A. Exhaust stroke, that is. In the end of the power stroke, the exhaust valve opens. During this stroke, the piston starts its movement in the maximum volume position. The open exhaust valve allows the exhaust gases to escape the cylinder. At the end of this stroke, the exhaust valve closes, the inlet valve opens, and the sequence repeats in the next cycle. 4-stroke engine requires 2 revolutions. So this is PV indicator diagram. So in the intake stroke, it will be both the valves are closed. It moves from 1 to 2 in the graph. And next is compression stroke. It is 2 to 3. Here volume will be compressed. Cylinder will be decreases. Its volume decreases, and ignition will be just on. Because of ignition, the temperature rises from 3 to 4. This process is at constant volume. And 4 to 5 in a power stroke, here the engine will be starts working. When it reaches the 5 position, the valve, outlet valve will be open, and all burnt and unburnt gases, they will be expelled out. Therefore 5 to 6 is called heat rejection stroke, and 2 to 1 is called exhaust stroke. Stage 1. It is the beginning of the intake stroke of the engine. The pressure is near atmospheric pressure and the gas volume is at a minimum between stage 1 and stage 2. The piston is pulled out of the cylinder with the intake valve open. The pressure remains constant and the gas volume increases as further mixture is drawn into the cylinder through the intake valve. In a second stage begins with a compression stroke of the engine with a closing of the intake valve between stage 2 and stage 3. The piston moves back into the cylinder, the gas volume decreases and the pressure increases because work is done on the gas by the piston. Stage 3 is the beginning of the combustion of the fuel and air mixture. The combustion occurs very quickly and the volumes remains constant, releasing heat raising during the combustion, which increases both by temperature and the pressure according to the equation of state. Stage number 4. Here beginning the power stroke of the engine between stage 4 and 5. The piston is driven towards the crankshaft. The volume in the increased and the pressure falls down as work is done by the gas of the piston. Stage 5. Now the exhaust valve is open and the residual heat in the gas is exchanged with the surroundings. The volume remains constant and the pressure adjusted back to the atmospheric condition. Stage 6. At this point begins the exhaust stroke of the engine, during which the piston moves back into the cylinder. The volume decreases and the pressure remains constant. At the end of the exhaust stroke, the condition have returned to stage 1 and the process repeats itself. During the cycle, work is done on the gas by the piston between stages 2 and 3. Work is done by the gas on the piston between stages 4 and 5. The difference between the work done by the gas and the work done on the gas by the area enclosed by the cycle curve and is work done produced by the Otto cycle. The work times the rate of the cycle is equal to the power produced by the engine. The area enclosed by the cycle on a PV diagram is proportional to the work produced by the cycle. On this page, we have shown an ideal Otto cycle in which there is no heat entering or leaving the gas during the compression and power strokes. No friction losses and the instantaneous burning occurs at the constant volume. In really, the ideal cycle does not occur and there may be losses associated with this process. Otto cycle. A Otto cycle is an ideal thermodynamic cycle which describes the functioning of a typical spark ignition reciprocating piston exchanging. The thermodynamic cycle, the most commonly used in automobile industries. Top and bottom of the loop, a pair of quasi-parallel adiabatic process. Left and right side of the loop, a pair of parallel isochoric process. The adiabatic process are impermeable to heat, flows into the tube through the left pressurizing point. Some of it flows back into through the right rejected process and the heat which remains does in the sheet itself. And its explanation can be put it in a PV diagram and also in a TS diagram. The process in an Otto cycle, the process 1 to 2 is an eccentric compression of the air as the piston moves from bottom dead center to the top dead center. Process 2 to 3 is a constant volume heat transfer to the air from an external source while the piston is top dead center. This process is intermediate to represent the ignition of the fuel air mixture and subsequent rapid burning. Process 3 to 4 is an eccentric expansion with power stroke method. So in this way process 4 to 1 is also takes place. Conclusion. Otto engine is almost about 30% efficient but not 100%. Rest of the 70% is loss. And this can be represented by a cycle called Carnot's is called as Otto cycle. Here E to A is charging stroke, A to B compression stroke, B to C it is heat is absorbed, C to D working stroke, D to A rejected stroke. B to C heat is absorbed with amount of H1, D to A amount of heat is rejected to the sink of the amount of H2. The cycles are step by step I will explain. Charging stroke. E to A represents the charging stroke. The mixture of air and petrol vapor is allowed to enter at atmospheric pressure. The final volume is V2 at a temperature is T1. It is represented by the graph E to A. Compression stroke. A to B represents compression stroke. Volume changes V2 to V1. Temperature changes to T1 to T2. Temperature is increases while volume is compressed, it is decreases. Ignition stage B2C. Here spark is produced by the spark plug, pressure is increases, temperature also changes. Working stroke. C to T, gas expands adiabatically and the engine works. The volume changes from V1 to V2, the pressure and the temperature decreases. Heat rejection. T to A, pressure decreases and temperature decreases from T4 to T1. Exhaust stroke. A to E, gas completely discharged, volume is decreases. Now efficiency of our Otto cycle. Let H1 quantity of heat absorbed from B to C. It is amount of heat is absorbed is H1 and this process is at constant volume, therefore it is CV, specific heat at constant volume, and we are considering 1 kg of mass of substance we have taken, and temperature rises from T2 to T3. Therefore, amount of heat is absorbed is given by H1 is equal to 1 into CV into T3 minus T2. And amount of heat is rejected from T to A is given by H2. Again 1 kg of mass we have taken for an experimentation, it is 1, and the process takes place at constant volume, it is CV, and temperature is falls to T1 from T4, therefore the difference is T4 minus T1. We know efficiency of any engine is given by neta is equal to 1 minus H2 upon H1. H2 is amount of heat is rejected, H1 is amount of heat is absorbed. Therefore, if we substitute H2 and H1 in above equation, neta equation, therefore we have got neta is equal to 1 minus T4 minus T1 divided by T3 minus T2. Here the points A and B, they are in adiabatic states. Therefore, if we write the adiabatic equation, T1 V2 raised to gamma minus 1 is equal to T2 V1 raised to gamma minus 1. The points C and D lie an same adiabatic. Therefore, T4 V2 raised to gamma minus 1 is equal to T3 into V1 raised to gamma minus 1. Subtracting the above equations, T4 minus T1, that is T1 minus T4 into V2 raised to gamma minus 1 is equal to T2 minus T3 into bracket V1 raised to gamma minus 1. Therefore, gamma is the ratio of specific heat at constant pressure to the constant volume. Therefore, gamma is equal to Cp divided by Cv. And rearranging the terms, V1 upon V2 raised to gamma minus 1 is equal to T1 minus T4 divided by T2 minus T3. We are writing reverse manner, T4 minus T1 divided by T3 minus T2 is equal to V2 upon V1 raised to gamma minus 1. Therefore, efficiency further terms will be cancelled and neta is equal to 1 minus V1 upon V2 raised to gamma minus 1. Therefore, neta is equal to 1 minus 1 divided by V2 upon V1 raised to gamma minus 1, and rho is V2 upon V1. It is compression ratio, and where rho is adiabatic compression ratio, and therefore if the rho is 8 and nu is 1.4, and if you substitute the values in above equation, we have got the efficiency of petrol engine is around about 56%. This is all. Thank you one and all for your such an cooperation. Thank you one and all.